you get this outcome. Instead of saying frequency, you can say probabilities. As I said, from our point of view, it's the same. Good. I think I said everything. Now, let's suppose that let's go to the technical question. Okay, I have a flow duration curve. I need to design an hydropower plant. What is my design flow? Or I need to design a water supply system. What is my design flow? Okay, now let's delete everything and let's depict a big flow duration curve on this blackboard. Keep in mind that if I am asking you this question, if we are talking about a flow duration curve, it means that usually we have a demand of water that is higher than availability. Because if we knew that there is plenty of water, we wouldn't estimate any flow duration curve. If we take observations and want to make sure that there is enough water, it means that we have serious doubts on the fact that we have enough water to satisfy the demands. The water resources manager comes into play when, for some reason, there is not enough water to satisfy a demand. And in particular, if we focus for this, this technical explanation, I want to focus on an example of a possible water use. A possible water use, which is extremely relevant, is hydropower production. So let me focus on hydropower production. And let's suppose that we want to build a run-of-the-river hydropower plant. What does it mean, a run-of-the-river? It means that you are not building a dam, you are not storing water. You want to generate hydropower when there is water in the river. You don't want to accumulate it. This provides a lot of advantages because, without building a dam, it becomes simpler and simpler. Of course, the dam gives you more opportunity because a run-of-the-river hydropower plant can only produce energy when there is water in the river. If you build a dam, you produce energy when you need it. I already told you that you cannot store energy, so the dam of course, gives you more opportunities. On the other hand, as I said, run-of-the-river plants are extremely interesting because they have a limited environmental impact. So today, also because we already built a lot of dams and we don't have many more opportunities in the Western world. In the Eastern world, you have a lot of opportunities. You may have heard that in China they are building huge dams, and very huge, and also in Vietnam. And in the countries where they also had political problems before, now they benefit from a peaceful period and are building dams. But in the Western world, it's an opportunity that was already deployed, already, taking benefit from. So, there is an increasing interest for the run-of-the-river plants. Okay. So let's suppose that we have designed this run-of-the-river plant, and what is our interest in getting as much water as possible? Because, of course, the benefit is given by energy production, not only economical benefit, the benefit in terms of reducing CO2 emission and whatever. And therefore, if we want to take this benefit at most, we need to take as much water as available. So let's focus on this particular situation. Let's suppose that we have identified a location where we can build a run-of-the-river plant, and we want to estimate what is the max amount of water that is convenient to withdraw. So let's estimate the design flow that is more convenient. Okay, so of course we need to estimate the flow duration curve to understand how much water is available. So let's now draw a big flow duration curve Q, T, no, let's say Q, and D. Okay, D can be between 0 and 1, just to remain in a... And let's suppose that we have a curve that is like this. From here to something here. Okay, this is my flow duration curve. So, just a few considerations on cost-benefit analysis. I'm not talking in this course, in this subject, of cost-benefit analysis. Keep in mind that this is a very topical issue today. You may have heard, for instance, about the discussion on the TAV, the high-velocity train, from Italy from Turin to Lyon. They discussed in the previous month on the cost-benefit analysis. It's an extremely topical issue. It's something that traditionally was not dealt with in engineering programs. Today, I think there is the need that we engineers get more experienced in this, because also it's very complicated. It's something where research is working on. I just want to highlight a few concepts related to this particular case. So let's suppose that I see this flow duration curve, and then I may say, okay, it's certainly convenient that I design my turbine for producing hydropower. I design everything is needed to bring water from the river to the turbine for the highest flow, because I want to be ready to produce a lot of electricity when the flow is high. Okay, but then, look, if I design everything for this very high flow, it means that I need big pipes to bring water to the turbine. It means that I need a big turbine for something that is working for this design flow a duration of few seconds, maybe few hours. Is this convenient? For sure not. Why not? Because I spend more for building the plant for an advantage that every year is just few hours. And then, as I mentioned to you, the turbine, when it works to a lower flow with respect to the design flow, is not efficient. The turbine reaches the max efficiency when it works at the design flow. So it means that I am designing a plant that works at max efficiency for just a few hours, and the remaining part of the year, very low efficiency. So for sure, if I make a cost-benefit analysis, it's not convenient. On the other hand, if I go to the other extreme, I have a turbine that is working every day at the max efficiency, because this is a flow that is almost always present. On the other hand, the production of energy is very limited. So, for sure, it's not convenient. I spend less in building the plant, in maintenance, and the plant is working more efficiently, but it's a plant that works for a very small flow. Remember the hydropower, if you indicate the power that you get from a plant with P, the power is proportional to specific weight of water, okay? This is fixed. And then there is a coefficient of efficiency, which is about, the max is about 0.7. Now we have plants that work at 0.8, but okay, let's say, okay, 0.8. But you see that a reduction in efficiency of 10% means a reduction in power of 10%, so it explains to you why efficiency is important. And then here I have to put the design flow, QD, and the hydraulic head, what is the head, is the difference in elevation, in altitude, between the place where you get the water and the turbine. If you have much hydraulic head over the turbine, you produce more energy. Usually in run-of-the-river plants, the head is limited. But you see that the power that you get is directly proportional to efficiency and design flow. So if you design for a low flow, the power that you get is reduced. So it's clear that the most convenient design flow is in between the highest and the lowest, as it always happens in a cost-benefit analysis. Usually you are placed somewhere in between, because if it was not in between, the cost-benefit analysis would be very easy, probably would not be necessary. Okay, so of course, to determine what is the most convenient, you have to do this. But we have a rule of thumb. The rule of thumb says that for a run-of-the-river plant, usually, the optimal design corresponds to a duration of about 60 days, which means 60 days means, let's say 15, I want to give the right percentage, sorry, 15, 20. 15, 20%. This is our rule of thumb. QD. Good. This rule of thumb is particularly useful because when you design a water system, it means that usually you need to get some water from somewhere. And given that water is public, water is recognized to be a human right, so water is public, then the management of water may be delegated to the private sector. In Italy, it doesn't work like that. It's a mix. In Italy, we allow a mix, so the water manager in Italy is a mixed company. It's part public funds and part it's allowed to be private sector. We already discussed about this, you may remember, those of you who attended the first lecture, first or second. So, when you want to use water, you have to apply for it. You have to ask for what in Italian is called concessione, which means permission. It may be that the relevant authority says no. This happens many times. Many times when you apply for permission to get water, the relevant authority, which may be, depending on the water course, depending on how much water you get, depending on the water body from you want to get the water, maybe the local administration. Like if you want to take water from a spring for supplying your house, an individual house, this usually is the local administration, what is called municipality or comune in Italian. If the importance of the water source, water body increases, then the relevant authority may be the region, maybe once was the province, and then the region, and then the national authorities. So you apply for it, for this permission, and they may say no. So this means that usually when you design these plants, you first make a preliminary design. The preliminary design is necessary in order to apply for the permission. And then if they say yes, then you make the final design. So usually what we do is, in the preliminary design, we use rules of thumb, like we estimate the design flow by taking the flow corresponding to a duration of 15%. And then, in the final design, we make the cost-benefit analysis. Okay, so this rule of thumb is extremely useful. Okay, that being said, now there is another question, which is, what is the volume of water that I get from there? This is important because I also want to know what is the average flow. The design flow is the max that I can take for a plant. I also want to know the average. Okay, you may say, but this is easy to reply, because I already mentioned that the area below the curve is the volume that passes through the river on average in 1 year. So one may say, well, this is easy to reply. I take the area that is below the curve up to here, okay? And I don't want to highlight it because, but anyway, it's the area, it's this one. And I have to stop here because for flows higher than the design flow, I cannot get it. And therefore the area below here could be our answer. But actually it's not like so, because there is the environmental flow to release. We already defined what is the environmental flow. The environmental flow, an order of magnitude could be, for instance, like the river flow that corresponds to a duration that is equal to close to 1. So let's suppose that it's here. It's something like this, which is constant. It may also be variable in the season. Let's assume that it's constant. Okay. Actually, in Italy, it's still constant. For each river, a constant flow is identified. So at least, I mean, the area below the environmental flow is something that I cannot withdraw. So this is to be subtracted by my computation. Why did I stop here? The reason is simple. I'm not continuing in this range because I don't need to release this environmental flow when the flow in the river is higher than the water flow that I am withdrawing. So basically, I may say that I need to subtract from the total this part. And then what remains here is volume that can be taken in orange. Is this clear? So the area below the flow duration curve and below the design flow is the volume that I can potentially take. If I subtract the volume of the environmental flow up to the duration of the design flow, the area in orange remains the part that I can effectively, the volume that I can effectively take. But there is a critical zone here. Because, you understand why? You understand why? Because I cannot stop my environmental flow at this stage, here. Because I still don't have an excess river flow with respect to the design flow that compensates for the environmental flow. When there is full compensation, I mean when I am sure that the environmental flow is released downstream, even if I take the max flow, and it's released because there is an excess flow with respect to the max flow. Okay? The answer is not difficult. If this is my environmental flow, let me put it here. Okay? And then I identify a range of duration where I need to calibrate a little bit. I start decreasing the release of the environmental flow, but not stopping it. Okay? And in this way, I identified here a volume. Now, how can I take into account this fact in the estimation of my overall orange area? Simple. Let's mirror this volume here. So, mirroring means something like, let me, so mirroring in this way, okay, something like this. That's it. So at this stage, I can really say that the orange area is my withdrawn volume. Look, this is very easy, but it's not easy to teach and understand. But what I'm saying here is just a matter of addition and subtraction, not more. So it's very easy. And this is a typical question for the exam. And I ask it because, indeed, it just requires to be understood that you concentrate on it. Then it's very easy. And look, I am also concentrating on this because, as I said, there is today an increasing demand for designing these plants, run-of-the-river, small run-of-the-river plants, because they are environmentally friendly and they indeed can be a useful opportunity. And therefore it may happen to you that one day you get asked to estimate the volume that can be derived. It's very easy to do it with an Excel file or with R, whatever. And then you can estimate an average. So you already have an estimate of QD, which is the design flow. Design flow. Okay? Then you can get an estimate of, let me see, because I don't remember the symbol that I use. It's QMP. QMP. Yeah, QMP. QMP is the average withdrawn flow and then let me indicate with QM. Let me see if it's indeed QM. Yeah, QM. QM is the average flow in pristine conditions. Pristine means natural condition. Average flow in pristine conditions. Look, a question, possible nice question at the exam, take a note. Let me ask you, can you please show me the position of QM in the flow duration curve on the graph? Very nice question. Very easy, but not easy. Okay. Because it is interesting. I mean, you have already QD on the flow duration curve, so it's interesting to see, to depict on the flow duration curve QMP and QM. Okay, Now we can define two indexes which quantify my withdrawal. And the first is water is called water withdrawal index. And let's call it IC. IC or what? IC. And this is equal to QD divided by QM. Oops, QM. QM, average flow in pristine conditions. This is usually higher than 1. And then we can define, I call it EU. EU is, let me write here. EU is water use index. This is equal to QMP divided by QM. And this is usually lower than 1, of course, because you cannot get an average flow that is higher than the average available flow. You cannot get a higher volume of water with respect to the volume of water that is available. So this is always lower than 1. While this one can be higher than 1, and usually it is, actually. But not necessarily, so this may be also lower than 1. This is comprised between 0 and 1. Of course higher than 0, because otherwise you have no withdrawal. So these are interesting to quantify the impact in qualitative terms of the plant. Okay, now I think I said everything. And in the web page now there are a couple of examples. There is a map that is taken from Google Maps, and it's not a map, it's an aerial picture that is taken from, I don't remember if it is taken from Google Earth I think, that you can zoom, and it's river barrage that is on the Danube. It's a river barrage where they have hydropower plants. And it's interesting because it's a river barrage that is also built, it's a multi-purpose barrage, because it's built also for keeping the level of the river high to allow navigation. So they have also navigation, I don't remember how they are called, navigation, just 1 second. It's the translation of shiplock. They have shiplocks. It's the translation of conca di navigazione in Italian. And basically, it's a device that allows the ships to pass through a barrage in the river. And it's interesting if you zoom it, because you can get an idea of how this plant is organized. And there is another more technical example which refers to the run-of-the-river hydropower plant that is built on the Po River at Isola Serafini. And this is the only hydropower plant and the only barrage that is built on the lower Po River. The Po River, contrary to the major other rivers in Europe, is not presided by barrages. And the reason is that basically we didn't want, first of all, we didn't have a very strict necessity of barrages to allow navigation. the Po River is navigated. We didn't have, as I said, a strict requirement. In the Danube, they had a strict requirement. If they wanted to navigate it, they had to build barrages. Barrages are detrimental for the quality of the ecosystem for many reasons, and because they interrupt the connection, the ecosystem connection between upstream and downstream, and also they slow down the river flow, and therefore reduced flow velocity means increased pollution. And therefore on the Po River there were some proposals in the past to build barrages, but you know, there was an opposition for this reason, because we didn't want to decrease the quality of the river beyond what is already compromised. And, but there is indeed only one barrage. There is one barrage. It is at Isola Serafini, and the purpose is just for hydropower production, not for navigation. Sorry, I forgot to turn it off, so just give me 1 second. Chiara, ti chiedo scusa, sono a lezione, ti posso richiamare tra 10 minuti? Ti ringrazio, ciao. Okay, this is the vice rector, so I didn't want to just shut the phone down. Just 1 second. Okay, so as I said, the design of the river plant is a very smart idea. What they did is the following. There was, and there is still, a long meander in the Po River. The meander, you know what is a meander, it's something like this. Meanders originate naturally in rivers in the lowlands, because you know, the river looks for of course, looks for the part of the land that are placed at a lower elevation, of course. But the river also brings sediments, and therefore, you know, when the river flows along a given direction, then what happens is that it brings sediments, and then it raises the elevation of the old bed, and then after a while the meander is abandoned by the river. Typically during a flood is abandoned, and the river finds another way for flowing downstream. And basically in this meander there was it often happens that I don't know the technical term, I'm sorry, when we talk about the two curves that basically mark the beginning and the end of the meander. It happens quite often that they get very close, and then during a flood maybe that the river breaks the levees and finds its way downstream by just cutting the meander. So what they did here, given that there is a difference in elevation from here to here, because the meander is quite long, of about a couple of meters, what they did here is to build a canal and to put a barrage in the canal, and in the barrage there is a hydropower plant here. So basically they have a gate upstream, they also built a gate here, and then with this, or maybe this is not very clear, I have to keep it. With this gate, they regulate the flow that passes through the hydropower plant. And it is indeed a big plant. And what is interesting, it's included in my slides, there is a figure which shows the flow duration curve. Let me look at the figure because I want to make it similar. Okay, there is the flow duration curve, which is something like this. Q and D is something like this, more or less. Okay, and it's more articulated than you will see, but it doesn't change the meaning. And then there is the design flow of the hydropower plant, which is something like here. And then what is depicted here, it's interesting, is the varying head, because the upstream water level is something that is more or less constant, And here I am depicting the water level. So this is upstream water level. So I need another axis to depict it. Water level. Which is constant because upstream, basically, we have a gate that placed here. So we can keep the water level upstream the plant that is constant. The water level downstream is varying because it's the water level of the Po River, the undisturbed water level of the Po River. And the water level downstream basically is varying. With the low flows is lower, with the high flows is higher. So it's something like this. Let me use another column. This is the downstream water level. Okay? Downstream water level. Okay, and then we can print the head H that was highlighted in the previous formula, and that is something like, that is the difference between upstream and downstream water level. So it's something like this. This is the head. So what does this mean? It means that for the highest flow, you have a reduced head. So when the Po River is in high flow, you cannot increase the design flow of the turbine, and therefore energy production is lower. The head increases, and therefore the energy production increases when the flow lowers down, the natural flow.